This video is brought to you by Maximus, the Maths Club of NIT Trichy. I am Jayantika, a PG Maths student, and today I'd be trying to explain or introduce how complex analysis is used in different fields. So basically I'm going to be giving some motivation into why we studied complex analysis, and then we'll move on to studying a few basics of the subject. Right, so I'd like to start with uses in different fields. Right, complex analysis, as we all might know, studying here in, if you are from engineering background or a science background, you must know what complex numbers are. They use imaginary numbers, right? They use imaginary numbers like I. So why would we want to use imaginary numbers? Why would we want to work with them? Well, the answer is that the different techniques in complex analysis, they are literally there in every field possible. So like in computer graphics, you use conformal mappings. Conformal mapping is basically mapping a complex number, right? We'll talk about that later. And then fractal generation, all of that we use. Then it has uses in engineering, right? Like in electrical engineering for signal processing, then analyzing AC circuits, then in mechanical engineering, like for analyzing fluid flow and all, right? For analyzing vibrations, then for designing different control systems, right? That's how it is used in engineering. Huge application there as well. And telecommunications is basically completely complex analysis. All the signal processing, modulation, then all the filtering techniques, they all come from the theory of complex analysis, right? So that's why I didn't add anything here, because it's such a big it has such a big application here. Next, it has uses in economics and finance too, somewhere where you would not expect it to be, right? Like behavioral economics, economic modeling. Then in finance, like risk management, pricing models, all of that, right? So even in the business world, in economics and finance, we know there is a lot of predictions and all, and complex analysis plays a part in that as well. The next use is an obvious one, which comes from maths itself, in geometry, when you study different surfaces, and how do you find functions between the surfaces, how do you talk about the mappings between them, right? So complex analysis provides a tool wherein you can locally preserve the angles between the surfaces, and it's very useful in doing that. Then it also comes up in number theory when you study prime numbers, and when you discuss about the zeros of the Riemann zeta function, right? And where else? Okay, I've missed the most important or a big one, which is, I think, it is mathematical physics. Mathematical physics also uses it extensively, the theory of complex analysis. So with it being present everywhere, I think everyone should have a certain level of knowledge about the techniques that this subject presents to us. And with that, I'd like to start with the basics of it. We know that complex numbers, we can write it in this form: a plus IB, right, where A is called the real part and B is called the imaginary part, right? So if we represent this number by a Z, right, so we can say that the real part of Z is A and the imaginary part of Z would be B. So here I would like to introduce a new notation where we write A plus IB as a two-tuple and ordered pair A comma B, right? So when you do this, your your calculations look more ordered, right? It looks generally more neater. That's why. So how do you add and multiply different complex numbers? Well, multiplication, you do it like this, right? A plus IB into C plus ID. Then you multiply it. Clearly you can see that the real part would be AC, and I into I becomes -1, so minus BD. So AC minus BD, and the I terms remain, I into BC plus I into DA, right? That's what we have written here, and that is just equivalent to writing it in our new notation, which is as the ordered pair A comma B multiplied by C comma D, and we take the real part, which is AC minus BD, comma the imaginary part, which is BC plus AD. Similarly, addition of complex numbers is equally easy. A plus IB plus C plus ID, we just know that it is A plus C plus B plus D, right? So as an ordered pair, we would write it as this is A comma B, this is C comma D, and the answer would be real part of this A plus C and imaginary part of this B plus D. That's how we add and multiply different complex numbers. Then there is something called the modulus. Modulus is when you take the real part of the complex number, so which is A, you square it, then you take the real part of the imaginary part of the complex number, which is B, you square it, you add them both together and you take the root. That is called the modulus, and it is represented like so. Mod of Z we call it. Then we have something called the argument, and formally it is defined to be the solution of these equations. X is equal to mod z cos theta, y is equal to mod z sin theta. So it's basically argument is basically the value of theta that we find from this, right? And I shouldn't have written x and y, I should have written A and B, because that's what our complex numbers, real part and imaginary parts are. So using these few basics, you can already see that we can already do a lot of things, like the entire real line, right? We know the real line looks something like this, right? The entire real line can be represented by this ordered pair x comma 0, because what is this? This is just x plus I into 0. Then we can understand what is I. I is basically 0 comma 1, right? 0 plus I into 1, which is I, right? And so we have now defined how R looks like in our complex plane, right? It's x comma 0, and what now I, which is an imaginary complex number, it has some meaning to us now, right? Now so using only these few things, you can prove a lot of fundamental properties of complex numbers, right? Like that. So if you represent your complex plane like how you see the R2 plane, right? R2 plane. if you look at it like this would be your real axis, this would be your imaginary axis, right? So you can represent your complex number on this plane itself, right? So a point z, x, y, this would just mean that the real part of the complex number is x and the imaginary part is y. But this is not the only way you can represent a complex number. There is another way, which is the polar form. The polar form of a complex number, right? Now, what is the polar form? It is basically like this. Z, we know it can be written as a plus ib, right? And we can write it as the modulus into cos theta plus I sine theta, and this can be just written as mod z e I theta. This is called the polar form of a complex number, and in general the polar form is the more used because we can see more clearly on it, right? So if we draw a diagram, and if this is our real axis, this would be our imaginary axis, right? This gets changed, right? So I could have used this diagram anyway. So the point z here, which is x comma y, right, this gets changed into the polar form of our number, which is z is equal to mod z ei theta. And what is that? That is just mod z, we know it is the distance from the origin, right? This is basically the distance formula that you write, x1 minus x2 whole square plus y1 minus y2 whole square, then you take root over it. Now if we consider one of the points, say x2 y2, to be the origin 0 0, that would give us the distance from the origin itself. So this is our origin, we take this point z x y, right? So this is our mod z, distance from the origin to the point itself, right? This is the modulus, and this would be theta, the angle by which the point has moved from our this is the theta, this is 0 and this is pi, right? The angle, how much the point has raised itself from this horizontal line here. So now we have seen how to represent a complex number, using the usual drawing the real axis and the imaginary axis, right? This would be a complex number. We have seen how to represent it in the polar form using angles and the distance from the origin, right? This is z, this is the distance is mod z, and it has raised itself by the angle theta. This is 0, this is pi. This is called the polar form, and this is the usual form, right? But there is another way of representing complex numbers, which is called the extended complex plane, also known as the stereographic projection. The idea behind this is that rather than representing the complex number, on an infinitely increasing plane, right, can we bring it into a more compact form? Can we represent our complex plane as a compact set? The answer is yes. If you have heard about the extended real line, what is it? It's just the real line, and along with that we have negative infinity and positive infinity. So we know the real line does not actually formally have a number called infinity, right? But if you add this minus infinity and plus infinity to a real line, this becomes the extended real line. In a similar way, the complex number can be represented by projecting it onto a unit sphere. So you can see both of these are 2D representations of our complex number, but here, right, so my diagram may not be the best, but we can think of a complex of a unit sphere like this, right? Okay, so this is our unit sphere, and what we do is, if we think of this as our complex plane, this ground area, the flat area below, right? So if you map every complex number z onto a point on the surface of the sphere, right? Onto a point on the surface of the sphere, then you have a mapping, right? A mapping from z to capital Z. And in this way, if you do it for all the points, you will only be left out for one point, that is infinity. What happens when z tends to infinity, right? That we represented using this point. This point is also known as the North Pole, right? And the point infinity is mapped to the North Pole. So all the points on the complex plane, they are mapped to some point on the surface of this unit sphere, right? It's a unit sphere with its radius 1, right? And the left out point, infinity, those points go to N, the North Pole.